guys. The webinar will start in 1 minute. Let's wait for a while. Yeah, right now I'm still seeing someone joining in. Uh, if the question in the chat box, then your question will be answered after the presentation. Yeah, any related question welcome. Yeah, but I will answer all of your question toward the end of the sessions. Okay, and if you notice that the session has been recorded and also the presentation today, we can share to all of you, but please leave your feedback that you would need a copy of the presentations. And the feedback, I think, is gonna send out to direct to your email after the sessions. Right now, I think we have about like 40 something people joining in. I think yeah, it's a good time to start. Let me, okay, introduce myself a bit. My name is Thai Tian Tong. I am a regional technical manager for CAT IT. Okay. And today's session will be on Ansys mechanical workflow for acoustic and noise simulations. And right now, do anyone have any problem on seeing my screen and like hearing me? I'd like to check first. Is that the sound okay for now, or should I change something?
It's okay.
Thank you. Okay. Then we can start. Yeah. Okay. Our today agenda is slightly changed a bit on the sequence and also the topics. Today's sessions will be on like acoustic. What is acoustic like? And I will introduce you to some of the acoustic wave equations. And I have prepared for like workflow on Ansys mechanical and also a short demo on how to do it. Yeah. For sure, I do have a huge topic on what can we do on test and simulation data of this acoustic. And I would like to introduce to you also the Ansys sound where you can do acoustic analysis or what we call like sound analysis and specifications on it or Ansys sound SAS. I have a use case where we like couple both of measuring sounds and also simulated sound on Ansys sound SAS. Yeah, and the last section would be Q&A. Yeah. First of all, let's take a look on what is acoustic. Yeah, from Wikipedia, acoustic is a branch of physics that study of mechanical wave in like gases, liquids, or solids. Right? Yeah, it can be like vibration, sound, ultrasound, or infrasound. Let's talk about it later. But normally people will engineer will take a look on this one as like audio or noise control, where we where our focus is on like noise control for sure in the industry, right? And then actually this acoustic sound is about like sound generation, propagation, and reception, and also of the mechanical wave and vibrations. This is like what is acoustic. It means that it's going to be the study of generation, propagation, and receptions. Then if you take a look on the sound itself, right? The sound itself, right, is the pressure disturbance that human ears can hear it. We know that the sound propagation is called like acoustic, right, as we mentioned earlier. And like in this case, actually the sound wave will travel from speaker to our ears. The sound wave in this case, it is in what we call longitudinal wave as well. And how it propagates, right? If it is in solid, it's gonna be molecular vibrate. But if it is in fluid mediums, it is because of molecular exchange the momentum. It means that it like moving together. I mean, moving ahead together. And in the propagations of the sound wave, right? The momentum will exchange between like fluid molecular. Then this variations is known of pressure. It means that if we know pressure variation or deviation, then we know that is how sound travel from like place to place. I would say that way. Then if we would like to classify it or classify our acoustic study, right? Actually, the acoustic study can be categorized into two groups, I would say. First, it is aeroacoustics, right? And the second would be vibroacoustic, right? The aeroacoustic would be like sound generation from aerodynamics, and the free space acoustic, uh, where like there is no solid surface, the sound can be generated from a turbulence or a jet noise, or with a free space acoustic, right? With a solid surface. It means that it is like airflame noise or rotor noise or Pauli layer noise or cavity noise. The other one, which is like internal acoustic, which is like the noise in the ducts, muffles, or ducted fan noise that you can see is like kind of various of the acoustic, aeroacoustic type. And also, if we talk about vibroacoustics, right, it is generated from the structure itself. It vibrates, and uh, this one, right, actually, it is a couple between fluid and the structure itself. Because of when it vibrates, it transfer, or the sound wave will travel inside the medium of fluid as well. Then in this case, we need to do a couple, or actually inside Ansys mechanical, we do have I mean decouple analysis as well. Then that what I will cover for today on vibroacoustic side. Yep. Let's move it on to sound pressure or sound, right? The sound pressure is the local pressure that deviate from the ambient, and atmospheric pressure. caused by sound wave. It means that when the sound wave it propagate, right, it make the pressure deviate. That is the thing. It means that we can use, as I mentioned, right, we can the momentum has been exchanged between molecular or molecule, and then in this case we can use the CFD simulation to solve the wave equation. Okay, let's talk about CFD a bit. Yeah, then you understand on what it is. Because of the aeroacoustic we do have what we call computational aeroacoustics or CCA method inside our solver as well. Actually, this method, right, it solves the Navier-Stokes equation, and the sound generation and propagation, can be simulated by transients, compressible CFD, or on any domain, like as a source or receiver, and we can monitor the pressure deviation using a receiver. Yeah, that is the thing. Then, if we going into a detail a bit, right, on this CAA, right? Actually, it just so now we solve equation on like mass conservation and also momentum conservations. And we do have what we call a local speed of sound equation. When we like manipulate the first and the second equation, right? Just like deduct, starting from the first equation, deduct by the second, and also deduct by a local speed of sound. Then it end up with this form where we have a wave equation here, and also what we call like Hill tensor, which is like the convection term, turbulent term, and also enthalpy terms change there. This is like the Light Hill equation on 1952. Then, actually this is like the how our Ansys CAA solver do inside Ansys Fluent. Okay. If we moving on to a bit, take a look on what is the meaning behind sound pressure or acoustic pressure. You can see that we have deviation or pressure deviation, and ambient. It means that uh, uh, we can superposition of the ambient and also the deviations. Then, when take a look on linear acoustic wave equation from mechanical solver, right? It has been divided to be two equations or two types. First is like we have no flow or no mean flow, then it end up like this. And also if there is no frictions, right, x n equal to 0, then we can have a wave equation for velocity potentials. And this one, right, we can have what we call finite element discretization as this one, because of we can have like a pressure boundary conditions and also wall velocity conditions. And in this case, right, we can solve this one, okay, and then to get what we call a waveform as well. And but actually, like, as I mentioned, for mechanical solver or for structure side, right, or vibration acoustic side, I will say this way, we cannot avoid solving in terms of what we call structure coupling on acoustic waveform. From structure dynamic equation, right? Actually, the fluid, right? The fluid will act as the external force on this structural dynamic equation. And if you have a fluid equation, right, then the structure acceleration will be one of the term on the fluid equation this way. And if we couple both of them together, it end up like this, because we would like to solve this in the couple way. And as I mentioned, right, the structural acceleration is acting on a fluid equation, and also the fluid pressure is also acting on structural equation. This means it's already coupled together. How we can conduct this kind of simulation? We will use what we call harmonics analysis. And also we need to run model analysis to get the waveform. And if we would like to do on transients, right, we can do it as well. But right now, the tool inside Ansys mechanical is like this. It means that we can use what we call modal acoustic, and we can use what we call harmonic acoustics for couple and decouple analysis of the acoustic analysis in Ansys mechanical. If we take a look on this, right, interest of like pressure distribution in fluid, particle velocity or sound pressure level, and also the scattering diffraction or transmission radiation of the acoustic in Ansys mechanical. This can be done and can be probed or can be plotted inside Ansys mechanical using harmonic acoustic. I will go a bit on detail on what is modal acoustic and also what is harmonic acoustic. But before that point, then let's talk about what is the application that we can use Ansys mechanical for acoustic analysis. Then for sure we can do like on a sonar analysis, the acoustic counterpart of a radar. And we do have, we can do what we call room acoustic and concert hall. And then we can check for the sound pressure level at each locations. We can do what we call noise minimization, noise cancellations, and also underwater acoustic analysis. And for sure, we can do on, we can simulate on to help on the design of speakers and also acoustic filter and mufflers. When we talked about acoustic, right, let's understand on what variable that we should take a look on. For sure, pressure, because of acoustic or sound pressure or acoustic pressure, it is a deviation of the pressure, right? A velocity and temperature and also the density of the mediums, and for sure that we need to take account on it. For the one that may not really familiar with sound, right, level, let's discuss a bit on this. How can we measuring sound? Actually, sound is measuring using a decibel scale. What is decibel scale? Yeah, okay. Then we need to understand this one first. That our human hearing range of pressure would be from this, like 0.0002 Pascal to 20 Pascal. And also the frequencies range from 20 Hertz to 20,000 Hertz. And in this case, right, we need to like convert this the pressure level on to be like easily understanding by using logarithmically sound power. Yeah. In this case, right, we have two, it's been like 3 decibel, right? This is like the thing. And actually the decibel scale is applied as a ratio of sound pressure or sound power to reference value. It means that we should have a reference value first, and then it's just like calculate based on the reference value. Then actually for the sound pressure, it is like 20 log tenths and the ratio. And in this case, the factor of 20 comes because of the sound pressure is like propagation to the square of the sound pressure ratio. Yeah. this is like how we like measuring the sound. And actually, like you have heard that we are using the word of sound pressure level, like, and the sound pressure level is defined by this or are calculated by this way. Okay. Yep. It's just like a ratio of pressure IMS divided by pressure reference. Then it's going to be the sound pressure level. And if you would like to feel or to understand more or get into a human feeling, right? Let's talk about what is the level or sound pressure level of some situation. Like recording room, a really quiet place is going to be like 20 decibel up to 140 decibel for like jet takeoff, right? Oh, yeah. But in a noisy place, like where we really yeah fell into, it would be like from 7 to 80 decibel. And if you read the article, where you will know that at this, I mean, more than 80 decibel will hurt, or I mean, or it will affect your health, conditions. Then, yeah, that's what is the thing. It means that our daily life would like fall into this, I mean, not more than 20 decibel. One of the things is that this is why sound pressure level is important to us then, and why we need to measuring it, or why we need to design or reduce the sound pressure level. Yeah, this is like one of the reason behind. Let's talk about frequency rating a bit, because of when you read the article or when you have seen the thing, actually the sound pressure level will have sound pressure level rating A or A ratings. What is the A rating? Actually, the A rating is the frequency rating for to actually is the frequency rating to make the sound pressure level match our ear response, I would say this way. Because of the human ear response, like is on 500 hertz to 8,000 hertz. Yeah, like that on, and we not really and we have a less sensitive to a low pitch and also a high pitch noise. That's why we need to rate it as a rating, which it is like to be matched with our hearings capability, I would say this way. Then I would put this way, that the frequency rating A is the sound level meter that related to our response on the human ears. That okay, yeah, you need to understand this one. Then come back to our Ansys mechanical. It means that we can plot for sound pressure level for sure. We can calculate for a rating for sure. We can plot or calculate or simulate for acoustic pressure for sure. And inside Ansys mechanical, it is divided to be two type of calculation. First, it is what we call modal acoustic. Second, it is harmonic acoustic. Then let's take a look on modal acoustic a bit. Actually, the modal acoustic is to determine a frequency and standing wave pattern or wave pattern within the structure. And actually, it can be within structure or it can be within the cavity domain or the fluid domain, because of in this case, right, we need to model both mechanical structure domain and also a fluid domain or acoustic medium domain, I would put this way. Then we have ability to include impedance and also the interaction between fluid as well. And actually the solver is available for like undamped Boclan-Chow subspace and asymmetric eigen solver, right? Then and also fully damped solver also available in this case. Okay, and actually in this image, right, it shows a standing wave pattern in an acoustic cavities or acoustic domain. Let me quickly show you on like model acoustic for this case. Okay, acoustic mode. Give me a second. We need to. Okay. What it look like? Yeah. First of all, what you need is this one. Yeah. Material properties. Yeah, we have like air property. Because of in this case, let me go back to this one a bit. So yeah, in this case, actually the cavity inside the cabin has been modeled, and then inside the cabin, right, actually it is air, fields of air. Then for the material, then we need to define as an air, and we need like density for sure. Speed of sound, you can see like viscosity. Yeah, and those two things, yeah, it's not that necessary for calculation, but yeah, anything that available on your data sheet, then you can fit it in. Actually, yeah, and then yeah, you just draw everything, and then let me show. I don't really draw and show you, but I will show you what is inside the geometry preparations and domain. Give me a while. It's gonna take a while to start Ansys Mechanical. Okay, actually, right, in this case, actually, we have draw the seed itself, and then we convert to be a fluid domain, or in the other word, right, we can call cavity, acoustic cavity domain or acoustic domain. In this case, right, I just like model this cavity and can define the material here, yeah, to be as, right, and after that, right, we just mesh it as normal on, yeah. We need to define, right, for model acoustic, right, we need to add this one. You can see that we have physics regions, and then we, yeah, because of we only have one bodies, then yeah, all bodies will be acoustic domain, as you can see. As you can see, yeah, and yeah. After so, right, in this case, actually, it's not that much. Then we can have what we call uh, a result of frequency and on also standing wave in each mode. We can have a various mode here. Actually, I can add all the mode. No, sorry, it should be acoustic pressure. It's not this one. Yeah, sorry. And I can just add. Okay, I can just add acoustic pressure, mode number 3, and then we can have a different mode of standing wave, and each mode will contain different frequency. If you compare to a vibration study, right, actually in this step, what we call it is eigenvalue solving for natural frequency, right? It contains both frequency and mode shape. That is for vibration, but for acoustic wave, it is called a standing wave pattern and also frequencies. You can see that is about approximately 100 hertz. The wave pattern will be this way. You can see, yeah, it can be this way. And for 113 Hertz, it is this directions for standing wave pattern. And for 160 would be this way. From the center. It's just like the way to calculate what we call a standing wave pattern. If we have a bit what we call that is only on the cavity, right? Actually, in the second case here, right, I have at what we call absorption surface, where we have absorption coefficient at 0.5. Then we can have different modes of acoustic pressure and also the pressure. I mean the frequency itself as well. Let's take a look this way. Then it is from without absorption layer. Let me show you. This is from no, sorry, should be this one, mode 1. This one should be mode 1 here. You can see that it is a bit differ from the frequency itself. And let me check whether it's about the same. I think the pattern is about the same, but the frequency itself is a bit different for the first mode. And if you would like to see what mode that has a different one, then we can just compare it. Let me the chart. No. Chart. Oops. It's quite a lot of things. We can. Okay. Give me a while. I need to only the frequency, then we can see it clearly from the table. Okay. So you can see that. When we have add the absorption surface into it, right, you can see that there's a slightly different on the frequency itself on mode 1, 4, right, 5, and 6 like that. It means that this absorption surface directly impact on this 1, 4, 5, 6 of the standing wave pattern. That is the model, acoustic model can be done or can be simulated for you. Okay, that's the thing for this model. Next, I will talk about what we call harmonic acoustic. Right. Let's go back to the slide a bit. Okay. Actually, for harmonic response analysis, right, is to calculate the response of the system as a function of frequency based on the volumetric flow rate and pressure excitations. And we can see wave propagation and also the sound pressure on each location. And actually, we can also plot or check for sound pressure level on particular location as well. And we can see what we call far field plot on the sound pressure level as well. Let me show you on this case. In this case, actually, it is audio speaker right here, and then we have an audio speaker. Let me show you. Maybe would be the fastest way, just like show you on what we can do on harmonics analysis, harmonic acoustic analysis. Okay, in this case, actually we have a speaker model here, and we have a plate that block the speaker, and this one is enclosed with the inside the block, a small box, I would say that way. Then in this case, we just for sure we need to add two acoustic domain. Yeah, first one, the second one, because of we have what we call PML layer here, then yeah, it will enclose everything inside this box, I would say. And then in this case, actually, I just add what we call vibration source or yeah, on this one, or mass source on this one, and then with this magnitude of this one, yeah. And in this case, after we sort it, right, we define this one, this speaker as a source of the sound, of the acoustic. And after we solve this case, like actually what we can plot, this is one. Let me show you this one. A sound pressure level. Yeah, it's quite hard to look. Right? Let me add the cross section and cross create section plane. Okay, and then my section plane. Okay. Oh, okay. I think I have created many times. I think this way. Check. Okay, it's okay. Just plot it's okay. Yeah. Yeah. Can see. Yeah. Yeah. From the speaker surface here, right, is propagate the sound pressure level. Nearby here is about 109 decibel. Yeah, and it like reflects on the PML surface as well. Yeah, you can see. But wait, for sure, it's like the contour plot of sound pressure level. I have plot as a cutting plane as well. Yeah, for easily see. Sorry. Yep. And if we talk about A rating, right? This is the A rating, yeah, or dBA. This decibel A, right? Yeah, this is what we call A rating. Nope. Plot. Okay. More than that, we can plot what we call far field. Far field. Oh, okay. Then when you take a look on this one, right? Yeah, we need to understand which. Uh, let me check. Okay, yeah. I should rotate this way. Then we have the proper location. Yep. Maybe I plot this. Let me use this one. On the top will be sound pressure level. Okay. On the bottom, I plot this far field. Oops, I think cannot. No, actually, so it's okay. Yeah. Actually, this is like at the toward front of the speaker surface. Then you can see that at in front we will have got a higher sound pressure level. Yeah, that's what is the thing. And if this is like the A rating from here, then the distance and also the angle like that. Yeah, this is what we call a far field plot. And actually the far field plot, right, we can define where is our sensor, I put this way, or monitoring surface as a sphere in at this 1 meter radius. Yeah, it means that if you stay away from the speaker for 1 meter, right, and you will get like yeah, in front you will have like approximately 71 dBA or decibel scale A, like that. Yeah, rating A. Yeah, this is like what we can do inside Ansys mechanical. And for sure, let me put this way. Yeah, you can plot a sound pressure level. You can plot acoustic pressure as well. Yep, you can see. There is thing. Yep. This is like what we call harmonic acoustic. Yep. let me go back to this one. Then let me talk about this one a bit. Because of our test is not like, because of we would like to hear the sound that came from our simulation as well. I would like to introduce to you on what we call Ansys sound, SAS, where you can listen to your sound pressure level that you have simulated from your simulation. Right now, we do have support on fluent, mechanical, and motion, and also LS Dyna. It means that if you can plot or extract what we call FFT data or the waterfall diagram, it looks like this from Ansys mechanical or Ansys fluent for FFT data, then you can import it into sound, and then you can listen to the sound that you have just simulated with. Then this is the case study that I have. Actually, for today, right, we quite have a short time period. I will show you on one of the cases where e-motor's noise has been simulated, okay, by using Maxwell, our electromagnetic solver, and couple with Ansys mechanical and export it to be waterfall diagram. And actually, right before that, let me introduce you to Ansys Sound a bit on what is the capability. Ansys Sound can do what we call sound analysis, order extractions, noise source separations, and psychoacoustic calculation, where you can get even the other indicator rather than only SPL or sound pressure level. For sure, we do have we can generate the sound from FFT data, from waterfall data, and you can use a mixer to design the sound or de-amplify or amplify it like that. Then actually, like, what is like sound analysis look like or order look like? Actually, the original recording will look like this. Is like a mess up. I mean, it is everything, right? But from this pattern, right, actually, we can separate it to be what we call engine sound and also wind and tire sound. In this case, actually, inside Ansys sound, you can do this, like separate this one easily by using what we call tachometers, tachometrics information models, and also we can create a data set or separate it quite easy inside Ansys sound. For psychoacoustic, I'm not sure whether your sound system is good or not. Actually, I play the sound of this one. Let me do it again. It is like the sound of testing aerodynamics for the vehicle, and this is the record of aerodynamic noise of one model. Let me play it again. Slightly lower. But when you like, actually from the record or the plot, like it seems to be about the same. But because of we do have the other indicator on psychoacoustic, then we can analyze that. These two types of design has different on loudness and also fluctuation thing. This is like you can identify by using the loudness and also fluctuation strength. Actually, not only that fluctuation strength or loudness, actually we do have the other indicator as well. In this case, it's just like a snapshot of psychoacoustic module inside Ansys sound. Actually, we have more than this. Get back to our point. I do have a short demo on as a video record here. When you using Ansys mechanical, we can see that we do have harmonic acoustic there, and then after we have done solving harmonic acoustic, Okay. We can plot for what we call waterfall diagram or sound pressure level waterfall diagram like this. Right now is a feature, a native feature there already in Ansys Mechanical. Yeah. Then we can just export it to be what we call XML data, and after that we can launch it inside. We can launch Ansys Sound and import that XML data in. And then we can get a web form. We can get a web, and also we can play and listen to it. Yeah, this is like how we do it. Let me show whether I can the add-on module. Yeah. Yeah. It's like the conditions. It's like right now. Yeah. This one is not like support because of this case is not the waterfall cannot port as a waterfall. We need to extend it, but you can see that the waterfall diagram is a native feature in Ansys Mechanical. Then you can just plot the waterfall diagram, and then you can have the waterfall diagram imported to Ansys Sound. Then let's go back to the use case. Let's go back to the presentation. I will give you the workflows on like solving emotional noise. For sure, this use case actually it is aimed to analyze the sound of electric motor based on Maxwell and mechanical. We would like to visualize the shift and reshape the sound. Yeah, and also we would like to compare between original and modified signal and using what we call psychoacoustic criteria. In this case, actually, it has been done on Ansys Maxwell, which is our electromagnetic solver. And then in this case, we just solve for electromagnetic force in transient analysis, and then it coupled with Ansys mechanical structure in order to solve response for each speed and RPM of the RPM, and we would like to create what we call equivalent radiated power or EPR. And after that, we couple with vibroacoustic and calculate for sound pressure level with frequency diagram on the waterfall diagram with multiple RPM as well. Then it ends up at the end we have got this waterfall diagram and import to Ansys Sound SAS. Yep. Okay, let's see the workflow. Actually, right, electromagnetic force calculated and then transfer and mapping on Ansys Mechanical. This will help us to calculate for mode shape analysis or modal analysis. Right? Mode 1, 2, 3 is okay. After that, it's coupled with like acoustic domain, and then we calculate for sound radiated or sound propagations. In this case, we can have what we call EPR versus frequency on RPM. And this, like, at the end, we export it as XML files. Right? Actually, that waterfall diagram has been exported to XML files. And in this case, actually, the spectra data we can import into Ansys Sound. And after this, after that, we can listen to it. This is from the waterfall diagram, and we can convert to be a wave sound. And this whistling sound, right? I'm not sure whether you have heard of it or not. I can play it again. We can do further analysis on it. As because we have got everything on Ansys Sound, then we can check for sharpness and loudness. And actually, the sharpness it is a sensation of the sound being really bright or with usually more high frequency content. For the loudness, right, actually is like perception of the sound intensity. Yeah, then yeah, we can have like this is like what we call sharpness versus sound, and also roundness versus sound. Yeah, if you take a look on the web plot, right, this one, you won't see the sharpness and loudness in the other perspective of analysis of the sound quality. But with Ansys sound, you can have this, right, that you know that the sharpness is high at this period of time, and also the loudness is quite high towards the end of the record. I just put this way. Then, if we go back to the waterfall diagram that we have just imported into Ansys sound, we know that you can see that here, there, it's quite red. It means it is a high level of sound pressure level. Okay. Which means that we can just off the peak, we can have this or the peak that we don't want. Actually, we can do it more than this for all of them. In this case, in this use case, they just like pick these four of them and then de-amplify. De-amplify means just turn it off. Just turn it off, something like that. Let me... Okay. Just turn this off, and then we can re-record this one and compare to each. Compare the modified signal with the original signal. In that, we already know where should we the case. We should like get rid of the higher loudness and sharpness. Then with this psychoacoustic indicator, it helps to categorize the sound quality as well. And the product design can have this psychoacoustic criteria to be the goal of the optimization for doing design better. I will put this way. If you would like to still here, you can play it. This is the original simulation sound, and this is the modified signal. You like notice that there is a big difference on both of the signals. Between these two signals, I would say. This is like my use case actually for this one, for the Maxwell and mechanical. Okay. Toward the end, actually, we can have Ansys mechanical to run for vibroacoustic, aeroacoustic. It will be on CFD solver, and or this one way, if we can export it to be waterfall diagram or AFT data, it can convert to be web form or web files that you can listen to it. And I can give you the other things that Ansys sound can enable you to listen to the analysis and design sound sort of based on real record and also the acoustic simulation result. This is Ansys sound capabilities in quick way. Last slide of mine. It is on. I just would like to give you the whole idea or the overall pictures of our Ansys ecosystem for sound analysis. I have mentioned that aeroacoustic would be on Ansys Fluent. Vibroacoustic would be on Ansys Mechanical. If you would like to listen to the simulated sound or acoustic level or sound pressure level, you need Ansys sound. Then at the end, actually, most of us would like to have optimized product, and then the psychoacoustic indicator can be one of the criteria inside our optimization. In this case, we need for Ansys line to be the engine of driving everything and optimize the product for you. Ansys line is the advanced tool for optimization and content optimization. That is the thing on my mind right now. I would say thank you for your time and for today. Right. Okay. Thank you. And if you have any question, please leave it in the chat box. Okay. Then I will walk through your questions. Okay. It seems not to have any question for me. No question. It seems no question for me. For sure, if you would like to have a copy of this presentation, you can drop your request on the feedback that we have got. Maybe the question is coming in. Let me take a look. For sure, slide will be shared individually, but you need to write a comment on the feedback. Okay. I would say that if we have a sound pressure level, right, and we would like to simulate it, I need to check on Ansys Mechanical. It should be done in Ansys Mechanical. Because we do have like a sound pressure level as a source of acoustic. And then we would like to see the propagation and radiate a wave, a sound wave radiated. And okay. One other question is on how can we consider like half air and half liquid filling into cavity. Right? Actually, if you can model, if it really a flat surface or half, we can model both, and then we can define both both cavity domain as a different material. I will put this way. I would say yes, we can. We can consider half and half liquid together. How to convert inverter to Ansys? That one we need. Even not mistaken, you need Maxwell. You need Maxwell. And then we can model or we can we can model the inverter inside Ansys solver, and then we couple the electromagnetic force onto mechanical, then we can simulate for the sound. Does this simulation also consider when conducting overall sound pressure calculation for plant? If we can define a domain of the plant or the power plant or industrial plant, where we can define acoustic source one place, and then yeah, we can do propagation calculation for sure. Yeah. Yep. Yeah, I would say for the silencer, yeah, we can run for the silencer. The silencer can handle, I mean, can be simulated by Ansys mechanical for sure. Yeah, the silencer simulations. Yeah. Well, okay. I would say I would only take. I mean, I would like to end at this point. For the other question, I will reply yeah, after this, because of yeah, yeah, yeah. Okay, for the one who requesting for the a copy of this presentation, please leave your comment on a feedback form where we will send to you shortly. But by the way, if you leave in the chat box, I will take a look as well. Yeah, and I will let our marketing team to send you individually. Yeah. Okay. Thank you for your time today. Okay. Thank you for your yeah, participation today.